In this video, we'll take a look at how we can begin to kind of expand and generalize upon some of the stuff we saw in the last video with tree diagrams and calculating probabilities. One important thing that we noted is that in part D of the last question, we saw that the probability that we were looking for was not shown already inside of the tree diagram. And that actually happens fairly often with some calculations. As I state here, part D of the previous example illustrates how conditional probabilities that are not found within a tree diagram can be computed from information that is presented in the tree diagram. Well, that leads to the following rule of probability, what's called Bayes' rule. Now, you can see here that at the start, we just have a simple conditional probability, like we did here. And you'll see that we even started this exact same way. We said that if I have a conditional probability, I compute the AND of the two events over the thing that's given, just like we did up above. Now, what seems kind of strange is this next step, like where the heck did this come from? But you'll notice that this is just exactly how I read information off the tree diagram. To get this top value of the AND, like we did up here, I just went down each of the different branches. I multiplied probability of M times the probability of U given M. And that's all that we're saying up here. Notice in the denominator, I had to do the same thing. To find the probability of the single event, I had to go back to my tree diagram and find all the times that I could have selected U's. So I'd have to do probability of F times probability of U given F. That gets me this value. Probability of the 0.6 times the probability of 0.06, or male times unemployed given male. And when I added those two results together, just like here I'm adding these results together, I get the denominator. In general, this is just a really messy looking formula, and for the most part, you can completely ignore it, because you will just almost intuitively use the formula without ever actually thinking of how it's expressed. What we can see here is that, again, all we're really using is the multiplication law and a law of total probability to re-express this conditional probability. What becomes kind of interesting, though, is that this event, B complement that's written down here, could actually stand for any number of separate individual events. And so Bayes' theorem can be expanded, and our tree diagrams can be expanded to account for scenarios with more than just two outcomes, more than just like male, female, or A and not A. We could actually expand into a lot of different options. And to see that, let's take a look here at example number 3. In example number 3, we have a warehouse receives widgets from 3 different manufacturers. Okay, so a widget just, I don't know, it's some item that, these different manufacturers are creating. And they all get stored in this warehouse. And, maybe they get shipped out to stores or something afterwards. Well, say manufacturer A produces 50% of the items that end up in this warehouse. Manufacturer B produces 30%. Manufacturer C produces the remaining 20%. So 100% divvied up total. Suppose that 2% of the widgets come from A, and they end up defective. So sometimes when manufacturer A makes some stuff, they're good items, and sometimes when they make it, they're not so good. 4% of the widgets, though, that come from manufacturer B are defective, so manufacturer B doesn't do as great of a job. And manufacturer C, well, they're like the worst, because 7% of the things that they send out are just totally busted and not going to work well. Well, let's create a tree diagram to kind of model what's going on here. Notice that I'm starting with thinking about the fact that I have a widget that's going to be coming from one of my different manufacturers. I have manufacturer A, manufacturer B, and C. And so I can think about the breakdown of how the widget gets sent out to these different, how the widget comes into the warehouse. 50% of the widgets come from manufacturer A, 30% come from manufacturer B, and we know that 20% come from manufacturer C. Again, along this splitting of the tree, I end up with a total of 100%. Now, once that happens, I know that there's another split that can take place, which is sometimes I'm going to get an item that is defective, and another time I may not get an item that's defective. So I get defective items, and we'll say not defective items. And that happens with each one of these manufacturers, defective and not defective. So I'll draw this out here. And notice I should be able to label some percentages on here, because I'm told that if the widget comes from A, there's a 2% chance that it's defective. If the widget comes from B, there's a 4% chance it's defective. If it comes from C, there's a 7% chance it's defective. Well, again, then notice that the split here should be easy or should make it easy to determine the chances that the items are not defective from each one of these manufacturers. Well, if there's a 2% chance that A makes a bad item, there should be a 98% chance that they made a good item. Similarly down here for B, I should have a 96% chance, and then a 93% chance for C. Once I have this, remember that I can go ahead and I can immediately begin to calculate all of my different ands by kind of moving along the different branches. So here I can calculate the probability of A and, oops, not and B, A and D, so A and defective, and I know that that's going to be my 0.5 times my 0.02, or what comes out as 0.01. Here I'm going to have the probability that a widget comes from A and is not defective. So again, that's 0.5, but now times 0.98. And so that's going to get me something like 0.49. I'm going to do this all the way down to fully build out my tree diagram here. So probability of B and D, it's 0.30 times 0.04. So this is going to come out as 0.012. Probability of B and D complement, that's going to end up with, let's see, 0.30 times 0.96. I have that as 0.288. Probability of C and D, so that's 0.20 times 0.07, or 0.014. And probability of C and D complement, 0.20 times 0.93, or 0.186. Again, I should be able to double check that at each splitting branch of the tree, I have a 100% split. And over here, as a grand total, I better end up with adding all these numbers together and getting 100%, which indeed I do. So now that I have a tree diagram, I should be able to answer each of these questions fairly simply. Part B, find the probability that a widget selected at random is defective. Okay, well let's see. Where are all the defective widgets? Well, if I go down these two branches, I hit defective. If I go down the B branch and then to here, I get to defective, and also down the C branch. And so I can actually then look at just all of these different probabilities listed out here. The probability that I ended at D would mean that I had to do A branch and then D branch. So this is 0.01. But I also have 0.012 and 0.014 for a grand total of 0.036. So there's about a 3.6% chance that any widget is going to be defective. So when I go to this warehouse, 3.6% of the widgets are bad. Well, now take a look at part C. Suppose a widget that was selected at random is found to be defective. So I pick up a widget at the warehouse, I see that it doesn't work, and now I want to go start hunting down, who's to blame? Did this come from manufacturer A? Did it come from manufacturer B? Manufacturer C? Who's responsible? Well, I may not know, but maybe I could calculate what are the chances that it came from each one of these people. Like, who would be maybe the most reasonable person to likely be mad at, right? So let's see. I'm going to calculate each of these. So I know that I want the probability that, what are the chances this widget came from A if I know that it's defective? Well, notice again, I don't have that information in the table. All I have in the table are what are the chances that something's defective given that I know where it came from. But that's not tough, because notice here then I can just go right back to how I always calculate conditional probabilities. And the two events together divide by the probability of the given. And since I just found the probability of the given here was 0.036, I'm pretty much done. Let's find the probability of A and D. Oh look, I already found that. That's my 0.01 up above. So if I crunch this out, I get down to a value of, let's see, roughly 0.2778. Okay, so there's about a 27, 28 almost % chance that it came from manufacturer A. Pretty good chance, but let's see how manufacturer B shapes up. B given D, that would be my probability of B and D over probability of D. Well, probability of D is 0.036. Probability of B and then D, well, that's 0.012. 0.012. Well, if I crunch this out, I think I end up with a value of 0.3333. That's a third. So, more likely that it came from manufacturer B than manufacturer A. Let's take a look at the last one. What about the chances that it came from C if I know that it's a defective item? So that's C and D over the probability of D. So I have 0.036 in the denominator. And I can see here that going C and then D results in a grand total of 0.014. Or if I write that out, it looks like this is a 0.3889. So if I was trying to think here about, which person is it most likely going to be from? Seems like it ends up most likely being a person, or being a manufacturer C. Okay, there we go. Now, there's obviously a little bit of complexity to creating these tree diagrams, to thinking about how you create them. A lot of times people will attempt to start creating them and put, where D's and A's and B's are in the wrong positions. Well, a lot of this just takes practice to get used to. To help with that, there is a worksheet for this section, but I also have included 2 additional problems that I'm not going to go through in these videos, but that you can look at in the lecture notes up online. Example number 4 talks about individuals in a population who have a particular disease and how could we test for that. We also have an example here of aircraft that gets lost and has locators, and looking at those sorts of scenarios. I would highly encourage you to go through these before you even try the worksheet questions, just so you can try to polish up the rest of your notes and see how these sorts of questions work and test your understanding. Then, of course, go take a look at the worksheets and try even more questions. With a lot of practice, you'll get really good at this, and it won't actually be that difficult. And of course, in the meantime, if you happen to have any questions, by all means, please let me know.